Yeah, how's that? I can talk. All right.
Okay, like about 10 seconds. And you're live.
All righty. Hello, good morning. My name's Jim Flock. As the title states, I'm here to talk about DIY, do-it-yourself green energy. It's a small-scale solar project that I began in my backyard. So the purpose is to describe to you all about my non-grid tie solar recharging station. This to be used for night lighting. That's the total scope of the project is nothing at this point. Is nothing more than having deck lighting so I can see to get in my house when I come back to the pubs at night. My background is in HVAC systems experience. I'm currently an electrical engineer, and I do RF antenna design for Philips. And what really got me started in this whole green energy thing was I attended a seminar about 5 years ago now, sponsored by Green Energy Ohio, on a solar panel workshop, where we actually installed solar panels on a local architect firm. And my philosophy for this project is just build it instead of just talking about it. Because I've been talking about this for like many years, and all the nuances and intricacies I could do, the details, I get killed in the details. So I said, let's just build something. And I didn't really design this from the front end. It's more designed through experimentation. So at this point, it's really just a kind of a kludge from a design perspective. So, but the rough specifications are, I've got a 120 watt solar panel. It's a polycrystalline panel. I've got a nominal voltage of 12 volts, and I provide about 10 amps of current. The estimated cost at this point, with just the bulk hardware, the solar panel, the batteries, and the charge controller, and some of the copper to get from point A to point B is about $600. So it's a little bit pricey for just a simple deck lighting experiment, but it's fun, so I do it. So this is basically the system overview. I've got the panel, the charge controller in series with it, and that delivers the power to the battery. And then I have, of course, a fuse in series to the load. And right now the load is just some random assortment of LED bulbs and a fan, a computer fan. So how do I begin this project? I begin with mechanical mounting. That's the first and most important part of any kind of solar design project. What I was able to do, my neighbor, and kind of keeping with the spirit of this do-it-yourself theme, was that I wanted to kind of harvest everything as local as possible, other than the solar panel. I couldn't harvest that locally unless I stole it off of a sign on 71. But I ordered that from Arizona, and a charge controller from Arizona as well. But the fabrication for the structure was fabricated down at a shop on 55th by my friend. And that design is actually the design of the structure. The frame is actually the coolest part about it, because what he did is he took all the wood and he centered it right in without any like high-tech tools. He just centered it right in the middle. So the center of gravity, actually, it translates all the weight is translated to the deck down there. So it's a beautiful design using just recycled or reclaimed metal. And it's a aluminum cast frame. It's 2 foot by 4 foot, so no rusting to occur there. And it's mounted with one Allen bolt, so it's really easy to take off. Subsequently, because it's so easy to remove, and because I live in Slavic Village, I had to put a chain around it. So now I have a big chain link chain over it with a big lock. So because silicon's in high demand right now, so worldwide. But I don't know if anybody really realized that down there, but whatever. So it's a fixed position, and it's at a 45-degree angle. It's about 20 feet off the ground, so it's on a deck. sits there. And it's facing the south. What I initially had it was I was facing it south. This is facing south in this picture here. But I subsequently turned it to a southwest sky. Seems to get good results there. The powerhouse. This is where the batteries are stored. And I wanted to keep something that would keep the precipitation off of the electronics. So I went to the local store down the street and got a Tupperware bin. It's not flame rated or ISO approved, but it does the job for now just fine. And the cost was within my budget. What I did there is I drilled a hole in the side just to vent hydrogen buildup when the batteries are charging. And I have a fan in there. It's an induced draft fan, and I'm going to put a filter on the other side eventually just to keep a nice constant airflow while the batteries are charging. Then the panel, the manufacturer is a Kyocera. It's 120 watt. It's actually, the title's Kyocera 120. It's a 2-foot by 4-foot module, and it's a polycrystalline silicon type. And the life expectancy on it panel is 30 years. And that picture there is actually, it's mounted to the and the black box on the right side there is the where the power is inputted or outputted. I had a choice. I could go with a amorphous panel, which may be a better choice for Cleveland because of the more gray skies we have here. But I chose this polycrystalline panel based on my Green Energy Ohio experience. That was the panel that we installed on the architect firm. And it seemed, when you read all the reviews on the internet, it seemed to be that panel, for the price, it seemed to deliver the most power and efficiency for the price. And it was a nice compact 2-foot by 4-foot design. So I said that's a good start in place. Then the charge controller, I could have designed this, but it's actually a really simple circuit. But for $50, you can purchase a Sunsaver, a 10 amp, and just put it in line, and they guarantee it for 15 years. And the point of the charge controller is just to maximize the battery lifetime. You don't necessarily need this component to make the solar system work, but batteries are kind of finicky. I don't think, from what I've read on the reviews, no one really understands batteries for solar systems. I mean, they're really cantankerous as far as the climate they like. They like a constant temperature, and they definitely don't like to have power inputted to them in big pulses. So with the charge controller, it limits that at a constant rate into the batteries. So the idea is to extend the battery lifetime. Then the batteries, from what I purchased was golf cart batteries, and they're 6 volt each, and there's a 228 amp hour rating. And the reason I purchased them was because from everything I was reading was that these were the most durable batteries to use for this type of application, based on the fact that they're good for deep cycle charging. They can run all the way down, and you can just pump the power back into them, and they won't die, so to speak, so soon in their life. They can handle that deep cycle charges. And I think golf carts also, the golf carts batteries can handle that temperature swing that we experience here in Cleveland. And of course the fuse, I put a fuse in series with the batteries to the load. It's a 10 amp barrel line. But the interesting point about this was that when I was putting this together, and this is definitely in tune with the DIY theme, was that you can have, when you're doing this, when you're doing these solar circuits or solar applications, a lot of the components that you purchase off for DC or 12 volt systems or 24 volt systems are rated. The standards have a higher quality than nominal 120 volt systems. So subsequently, the cost for components like breakers or disconnects is much higher than a standard 120 volt system. So I didn't necessarily purchase a fuse block that was rated. I made my own, and what I did is I took a PVC holder from like an electrical box for outdoor wiring, and I took some what you call sockets, light bulb sockets, like they're for like LED light bulb sockets from electronic surplus, and integrated those into this PVC holder and put the fuse in there, and that actually is a nice press fit, and that actually works pretty well as a fuse. So it's really kind of really do it yourself, but it's functional. And I can make more of them as well, because it's not a problem. But then I have a switch, and currently I just did a regular single pole switch, and I mounted it in an outdoor environment with the PVC. But eventually I want to get to a photocell and a motion sensor, which I haven't done that yet. That's the plan. That's the future plan, is to actually put a switch in series with that, and then you'd leave that one in circuit, and then you have the motion sensor and the photocell in series with that, and that would just be your active switch then. And the load, currently I have only a few of these type of handmade LED light bulbs, which I'm positioning around the deck to give lighting. So I maximize my lumen output by parallel LEDs. So so even though the effective lumen output of each one is low, you've got a bank of them. It actually lights up the deck good when I come home at night. And the future goals for this project is eventually I want to get to characterize the charging cycle of the batteries. And I want to design this low power RF switch for motion and photo sensing. And I definitely want to improve the lighting fixtures. And I'd like to implement some type of GUI, like a kiosk, like that would tell you, like it'd be interactive type of station, which would tell you exactly what the batteries are doing at the time, and you could chart, you could track actually the sun daily, and log it and put it somewhere on some kind of database. But that's at the rate it took me to do this project, that's probably going to take me like 2 years, but maybe 5. But any questions? Anybody want to talk about RF receive antennas? That's actually what I'd rather talk about than. But if you have any questions, feel free. The solar panel itself cost $450. The batteries were $75 a piece, and the charge controller was around $50. So it's pretty.
What's the output of the panel?
It's 120 watts.
120 watts.
Yeah. Thank you.